Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today we're diving deep into the fascinating world of compression algorithms, a topic explored in a recent article, taking a look at compression algorithms. Let's get started.
I'm eager to hear this. The article mentions several algorithms. Which ones are we focusing on?
We'll cover the main ones: gzip, Snappy, LZ4, and ZSTD. The article provides a great overview, but also delves into the nitty-gritty implementation details, which is really exciting.
Excellent. So let's start with gzip. What's the core idea behind it?
Gzip uses the deflate algorithm, a combination of LZ77 and Huffman coding. LZ77 finds repeating sequences and replaces them with pointers, while Huffman coding assigns shorter codes to more frequent symbols. It's incredibly efficient, used in many file formats like zip, docx, and even PNG images.
That's impressive. The article mentions cabin fever in relation to DEFLATE's complexity. Was that a joke?
Yeah, it was a humorous anecdote from a YouTube lecture the author mentions. It highlights just how intricate deflate is at a bit level. It's a testament to the ingenuity involved.
I see. So how does deflate's LZ77 implementation work in practice? The article mentions a chained hash table.
Exactly. It uses a chained hash table to efficiently find matching sequences. It hashes sequences of bytes and stores them in linked lists. When searching for a match, it checks the hash table, then traverses the linked list to find the longest match. The further it searches, the better the compression ratio, but at the cost of speed. It's a beautiful balance.
Fascinating. And what about Huffman coding within deflate? How does that contribute to the compression?
Huffman coding takes the output of LZ77, the literals and back references, and assigns variable length codes based on frequency. More frequent symbols get shorter codes, leading to further size reduction. It's a two-pronged approach for maximum efficiency.
Got it. Let's move on to Snappy. The article says it prioritizes speed over compression ratio. How does it achieve that?
Snappy is much simpler than deflate. It uses a much smaller hash table and only considers the most recent match, sacrificing some compression for speed. It's incredibly fast, with compression and decompression speeds often exceeding 250 megabytes per second and 500 megabytes per second respectively. It's a trade-off that's often worth it.
Amazing! The article also mentions LZ4. How does it compare to Snappy?
LZ4 is very similar to Snappy, also prioritizing speed. But it's even faster, often outperforming Snappy in both compression and decompression engagement. It uses a similar LZ-based approach, but with some clever optimizations. The article shows some impressive benchmarks.
And finally, ZSTD. What makes it stand out?
ZSTD is a real game changer. It manages to achieve compression ratios comparable to or better than deflate, while maintaining speeds similar to LZ4 and Snappy. It's a remarkable achievement. It uses a combination of LZ, Huffman coding, and FSE, finite state entropy, for optimal results.
The article briefly touches on FSE and arithmetic coding. Are those key to ZSTD's success?
Yes, they are. Arithmetic coding allows for a more precise representation of symbol probabilities than Huffman coding, but it's computationally expensive. FSE is a more efficient alternative that achieves similar results. It's a clever optimization that makes ZSTD so powerful.
That's incredible! The article also mentions trainable dictionaries for ZSTD. How does that work?
ZSTD allows you to train dictionaries on a sample dataset. The compressor then uses these dictionaries to find common patterns and improve compression, especially for repetitive data. It's a powerful feature for specific use cases.
So to summarize, we've explored 4 major compression algorithms: gzip using deflate, Snappy, LZ4, and ZSTD. Each offers a different balance between speed and compression ratio, with ZSTD standing out for its ability to achieve both high speed and high compression. It's been a fascinating discussion.
Absolutely. It's amazing how much ingenuity goes into optimizing data compression. Thanks for joining us on Tech Bytes and News. We hope you enjoyed this deep dive into the world of compression algorithms. Have a great day.
Bye-bye.